Geometry for Real People, Points, Lines, and Planes by Overlook Tutorial Academy. Geometry is a study of descriptions. It is the mathematical method for describing shapes and spatial relationships. Geometry begins with a network of definitions that are then combined to make other definitions that are then used in proofs of even more definitions. In this article, I will focus on the simplest definitions and relationships, those that deal with points, lines, and planes. Postulate versus theorem. Both postulates, also called axioms, and theorems define relationships. We couldn't get anywhere with geometry if there were not some things we could agree were true without having to prove them mathematically. Geometry does involve proving theorems, of course, but I will leave that to other discussions. I love proofs, but most sane people do not. This article describes the logic of postulates and theorems to help you understand proofs and work with them more easily. Point. A point is a specific position in space. A point has no dimensions. It is just a position. In either a drawing or a mathematical statement, a dot and one capital letter represent a point. For example, in Figure 1, A, B, and C are all points. Line. A line is a continuous set of points that extend in opposite directions from a given point for an infinite distance. In mathematical statements, a line is identified by naming 2 points on the line and usually drawing the double-headed arrow symbol over the letters that represent the 2 points. This convention can be seen in Figure 2. For text simplicity, this article will use arrow AB arrow as needed. 3 lines are shown in Figure 2, AB, AC, and BC. Points that lie on the same line are referred to as collinear. Line segment. A line segment is a piece of a line that ends at specific points. To identify a line segment, one can write AB with or without a line over it, as you see there in Figure 2. The points on each end of the line segment are referred to as its endpoints. Ray. A ray is a portion of a line that consists of a specific point, the endpoint, and the set of all points on one side of the endpoint. To indicate on which side of the endpoint the rest of the points lie, it is usual to designate another point along the ray. This way, the ray can be written AB arrow, or with the arrow above the letters, as you see in Figure 2. Line postulate 1. The ruler postulate. Number 1. Any 2 points on a line may be assigned the values 0 and 1. Using these 2 points as a gauge, all other real numbers can then be represented on the line. Here's the idea. There are an infinite number of points on any line. Remember, points have no dimensions. You pick any 2 and call them 0 and 1. Then you know how far apart are the points on the line representing all other integers. This process is referred to as establishing a coordinate system. Number 2. Once the coordinate system above is in place, the distance between 2 points on the line equals the absolute value of the difference between their coordinates. Basically, the distance between any 2 points in the units described in number 1 above can be calculated by subtracting one coordinate from the other and taking the absolute value of the answer. Line postulate 2. Through any 2 points, there is exactly one line. You can't fit more than one line, because, as we know, a point has no dimensions, just position. Line postulate 3. The line, plane, and space postulate. Number 1. A line contains at least 2 points. But then you knew that already. Number 2. A plane contains, or can be defined by, 3 points, not all on the same line. Look at it this way. A line has only one dimension, length. Think about that for a moment. All of the points lie one next to the other, and even though the points themselves have no dimensions, they do describe a length through the universe. No width, right? No matter how many of them there are on that line, their very skinniness means that the line can never have any width. It will take another point, one that is not on the line, to produce a plane, like a piece of paper. That is, to provide some width. Points, or lines, that lie in the same plane are referred to as coplanar. Number 3. Space contains at least 4 points, not all in one plane. Now, if you understood statement number 2, this one involves a very similar leap of logic. A plane has just 2 dimensions, length and width. The points that make it up are still skinny and still can't give it a 3rd dimension. It takes yet another point, one not in the plane, to impart the 3rd dimension, depth. Line theorem number 1. If 2 lines intersect, they meet at exactly 1 point. Sure, you have this one. The lines are too skinny to overlap in more than just 1 point. Line segment postulate 1. If point B is between points A and C on a line, then the following is true. A to B plus B to C will equal A to C, like figure 3. Line segment theorem 1, the midpoint theorem. If B is the midpoint of line segment AC, then it is true that AB equals BC, and AB equals half of A to C, and B to C equals half of A to C. A mathematical description of the middle. Take a look at figure 4. Plane postulate 1. Number 1. Through any 3 points, there is at least one plane. You know this from the postulate above that defined a plane. Now, number 2. Through any 3 non-collinear points, there is exactly one plane. This is here to remind you, by stating the opposite, that if all 3 points are on the same line, there are an infinite number of planes that contain them, in any and all positions in the 3rd dimension. Figure 5 shows just 2 planes out of the infinite number that intersect in space in a single line. A 3rd point is needed to define exactly which one of that infinite number of planes it is. Plane theorem 1. Through a line and a point not on the line, there is exactly one plane. You can see this one by remembering, if there are 3 points, there will always be exactly one line that includes at least 2 of them. This involves the same logic as in number 2 above. Plane postulate 2. If 2 points are in a plane, then the line between them is in that plane. The line has to go straight between the 2 points, and none of them, the points, the plane, nor the line, has any depth, so the line must lie in the plane. Plane postulate 3. If 2 planes intersect, then their intersection must be a line. You can see that this must be true from figure 5. Keep in mind that a plane, similar to a line, continues infinitely in both of its dimensions. No two planes can touch except in a line. Plane theorem 2. If two lines intersect, then exactly one plane contains both lines. Consider figure 6. You know from the postulates above that because they are on the same line, points A and B are in a single plane, because every point on a single line lies in the same plane. Likewise, points C and D are in a single plane. Now, if the two lines intersect at point E, then point E is collinear with all of points A, B, C, and D. Therefore, all of the points and both lines lie in a single plane. Final note. Every textbook writer numbers the postulates and theorems differently. I've tried to give them some vaguely descriptive names wherever possible. I have to leave it to you to apply the appropriate numbering from your text to my explanations. If you have any questions, feel free to contact us. And by all means, keep an eye out for other articles in this geometry series. And as always, thanks for listening.